Welcome to the shop. Well, it's been almost 2 years that I've had the mini mill in my shop, and I've made thousands of parts on it, and I thought it would be a kind of a cool thing to make a little bit of an update video to kind of describe how things are going, how the machine is working, and how it fits into my workflow in the shop. And the basic answer is, the simple answer is, the machine is great. I love it. It works exceptionally well. I haven't really had any problems with it. I mean, it works. It's reliable. I did have one small software issue, and I contacted Haas, and they corrected it and sent out a technician to install the new version. Evidently, they don't have online updating, so it took the technician a bunch of what seemed to be fairly tricky steps to get the thing updated, but everything is working exceptionally well, and the machine is just great. I've been using it mostly to produce the products that I sell. I manufacture machinery for glasswork, and my main product is the Inquala, not quite a lathe handwork assistant. I just introduced a new product, Octavius Squeezer, which is a little more specialized, a little more obscure, an even smaller market than the Inquala, which is already a small market because there aren't that many glass workers. And I do a bunch of other work too, a lot of prototypes, a lot of one-off, a lot of just experimental stuff, whatever tickles my fancy. And let me go over to the machine here, just in case anybody's interested. 10,203 cycles according to the cycle counter. And like I said, the machine has been working exceptionally well. I thought it might be interesting to talk a little bit about how I use the machine. A lot of what I do is production, but it's not large production. It's very small scale production. I typically make a run of 20 Inqualas at a time, and this usually means that there's a run of 20 of each parts. Some of them are more than that, but mostly it's small run production. And in small run production, sometimes setup time is really what determines how fast the parts get made. Sometimes the setup can take longer than actually running the parts. And so I've developed a number of strategies to minimize setup time and basically get as quick as I can from one setup to another so that I can get these parts out the door faster. These strategies involve a lot of things, mostly just to start from the basics. Most of the parts that I make are fairly similar. And this is actually kind of intentional. When I'm designing something, I design it with manufacturing in mind. I design it every time I design a part. I try to imagine, how can I make it? Can I make it on my machine? Is it going to fit? How many operations are there? How precise does it have to be? And if it turns out that I'm thinking of a design that can't be made in my shop, I usually try a different design that can be made in my shop. So that's the first thing, is just design for manufacture. And of course, that leads into a completely separate rant about how engineers that don't know how to make things are crippled, and engineers that understand manufacturing and who can design parts that fit well into the shop in which they are going to be made, then everybody has an advantage. The engineer has an advantage, the machine shop has an advantage, and everything works smoother. So first off, I design parts that a lot of the parts are similar in the way that they're made. A lot of the parts use similar machining procedures. And so the first step in minimizing setup time is to minimize the variation in the type of parts that I make. The next steps involve tool numbering, tool selection, using a reasonably small set of common tools, common screw threads, common hole sizes, common cutter types, so that I can pre-load tool holders with tools, measure their offsets, and put them in the rack. And so I don't have to constantly be loading tools, measuring tools, unloading tools, and all that. Next thing is work offsets and overall work style. I have a number of work offsets that I've defined that are all, they all serve a purpose, and they've all been refined over time. And if I make my parts using the standard work offsets, then I can avoid having to do a lot of extra special setup. And then the final step is probing. I have the Haas Renishaw automatic probing system that makes it very easy to set work offsets. It's probably the biggest factor in the shop in improving, reducing setup time. And I use the probing routines for pretty much all of my setups. So I'm going to move the camera and show a little more detail. When I first got the machine, I was slightly disappointed to discover that the tool changer had what appeared to be a very serious limitation at the time. Unlike the Tormach that I had outgrown, and unlike the larger Haas machines, the VF series and the others in the product line, the Mini Mill has a bizarre limitation where the slot number in the tool change carousel is assumed to match the tool number. So tool 1 goes in slot 1, and it's intended, at least in its standard configuration, that you don't put tool 50 in slot 1. Well, as you can see, I've got lots of tools, and being limited to only 20 tools just wasn't going to work for me. So when I made my original set of videos 2 years ago, and I was talking about this problem, I came up with the idea of standard tool sets, where I would kind of preload the carousel with the appropriate tool set for the part being made, and then write custom post processors for my CAM system to be able to specify which tool set to use. And this worked, but it turns out that, I didn't see the simple solution, because I ended up choosing the way more complicated solution when a simple solution was far better. After a little bit more custom programming, I reprogrammed the post processor for my CAM system, which is BobCAD. And yeah, I know I've read some of the comments that, why are you using BobCAD? Well, I'm using it because it's cheap, I know it, it works, and yeah, I may investigate other options in the future, but every one of them seems to have problems. Fusion 360 is subscription-based with no local storage, and I hate that. Mastercam is outrageously expensive, and it's not really worth it for a shop at my scale. So anyway, I figured out how to reprogram the post processor to do what I call sequential tool numbering, which is the simplest, kind of the easiest way to do it. I also probably should have said this earlier in this monologue. There is a setting that's in the Haas Mill configuration that allows a different tool length offset to be used, so that you can basically separate the H parameters and the T parameters. So you can say call for tool 1, but apply offset tool 50, and in the manual they say don't use this, it's dangerous. And of course I ignore that because the way I use it, it's perfectly safe. So now I have in the set of tool offsets, and yes, the Mini Mill does provide a database that has room for 200 tool offsets, and you just wonder why they didn't also include the software to specify slot number, but oh well, it is what it is. So I have each one of my tools, I've measured the tool offset, stored it in the offset table, and then programmed the post processor to sequentially, as the tools are called for, to I put in an option stop so that I can load the tool into the spindle one by one as it's called for, and then perform the operation. Works really well. It actually, you know, now that I think about it, I had gotten so used to the Tormach way of doing things that when the Mini Mill came along, I thought, oh no, this is bad. I wish I had the Tormach way of doing things. But now that I've gotten used to my sequential tool numbering in the post processor, it's actually faster and easier, and I like it better this way. Another thing that I've done that I think may be uncommon, I'm not sure how many shops do this, but every hole in my tool rack is labeled with a Dymo label, and every tool, see if I can get that on the camera here if the camera focuses, every tool has a label labeled with the Dymo label maker. And yes, they do survive 10,000 RPM and coolant for years. The labels, I'm actually using a Dymo label that's called the durable version, and it seems to work really well. And as far as I'm concerned, the tool change problem is solved. No big deal, and move on to the next thing. So the next thing is work offsets. I've configured a standard set of work offsets that pretty much cover all of the different possibilities, and I've also configured a standard set of probing routines. I know Haas provides the VPS templates that will create probing programs, but these programs still require a fair amount of manual intervention, and when I'm trying to save time and make my setup go faster, I don't want any manual intervention. I want to just load the probe and push the button and have it do everything. And of course, this kind of implies a few things. It implies that the vices will be mounted roughly in the same place on the table every time, and of course when I mount them on the table roughly in the same place to make sure that the probing routine has a kind of an idea where to start. And I also make use of a lot of what Haas and Renishaw calls protected moves, where instead of just doing a rapid move to a probing location where if there's an error in the move, or if something is changed, or if something gets in the way, it'll break the probe, a protected move moves slowly with the probe active, and if anything touches the probe tip during the move, it immediately stops and flags an error. So another thing that I do, in addition to the custom work offsets, I have a drawer here filled with custom soft jaws, and each one of these is milled out of aluminum. I mill both of the faces parallel using a shell mill. I mill the sides perpendicular to high accuracy, they're within 1/1000th, and then I mill a ledge also as accurately as I can do to act in place of parallels. There's two reasons that I don't like parallels and that I prefer my ledges on soft jaw approach. First off is that parallels are loose, and every time I take out a part, I blow it off. I blow off the vise. I blow the chips out. And with loose parallels, there's always a chance that a chip might get caught. There's also always a chance that the parallel might go flying if I hit it with the air nozzle at the wrong angle. And of course, yeah, there are spring-loaded parallel keepers, but that doesn't solve the second problem. The second problem is that when I'm drilling through holes, obviously the drill bit has to protrude from the back end of the part, and I certainly don't want to drill if I'm drilling close to the edge of a part. I certainly don't want to drilling into a parallel. That would really suck. So by having the ledge on the soft jaws, it means that there's no loose parts to get lost. I can blow it out confidently without any fear after I take a part out and put in the next part. And if a drill bit happens to protrude through the part and put a divot in the jaws, no problem. It still has a mostly flat reference surface. If the divot has a little bit of a burr, I can knock it off with a file. And I typically maintain two sets of jaws, where I have one set of kind of like pristine jaws with no divots, and the other set that's kind of like all dinged up, and I use them as appropriate because for some of the operations I do, I want to hold really tight tolerance on thickness, and for other operations, it kind of doesn't matter. If I'm drilling a hole, it doesn't matter if the piece is 1/1000th off the surface. In addition to the smaller set of soft jaws, I also have tall jaws that are very useful in some situations. For example, if I'm drilling in the end of a part, nice to have support all the way up to somewhat more accurately guarantee that I know where I am on the top of the part. And I also have some kind of special jaws for machining special parts. Something else that I recently started using is custom machined soft jaws that clamp into the vise. And in the past, I just made these little adapter plates that would hold a part into the orientation for machining. But the problem with these, they're loose. Same problem with parallels, that if I blow them off, I can get a chip under them. They're difficult to precisely get back into place within a couple of thousandths. And the precision machined soft jaws that actually are clamped into the vise don't have any of these problems. And now that I'm used to doing it and I have the procedure all worked out, it really doesn't take that long to make one. It's actually a fairly easy thing to do, and the aluminum isn't that expensive. So that's another incremental improvement as I continue in this adventure of CNC machining. When I first got the machine, I used the leftover Tormach vices that I had from the PCNC 1100, and they worked fine. They were okay. It saved me a couple of bucks, but they were small and limited. They were 5-inch wide with a 4-inch opening, and it worked for a lot of the parts that I did, but I was always running into problems where I didn't have enough vise. So I replaced them with a couple of nice Curt vices that seem to be much higher quality, just better vices in general, 6 inches wide with an 8-inch opening, and the way it's mounted on the table, I believe that I can get access to the entire 8 inches. So once again, trying to minimize setup time and make things go quicker, let me loosen up one of these vices here. I know that the Curt manual says never use a power tool to tighten your vise. Well, I don't use a power tool to tighten my vise. I use a power tool effectively as a rapid feed. So if I need to open it for some reason or close it, I use the power tool. I never use the power tool for tightening. I always get it just close enough and then grab the regular Curt handle and use my hand and try to be careful not to break my vise. So another tool that is very useful is this cordless ratchet. And since I change vise jaws a lot, this makes it a lot faster than trying to snake a hex key in there and work within limited range of motion and bang my knuckles and all the other awful things that happen when you try doing work like that. And by using this strategy, I can very quickly swap out soft jaws and then very quickly probe the soft jaws to find out where my 0 point is. On this particular setup, the 0 point is at the back surface of the soft jaw, the ledge, and the left corner. This is not always true because there's a number of situations where a different strategy is used. And let me get one of the jaws here. In some cases, if you're clamping a small part, let's say you were clamping this small part, you wouldn't want to clamp it on the left-hand side of the jaw because that makes the jaw kind of twist sideways and it's not recommended. So you want to clamp a smaller part closer to the center of the jaws, and to do that I've got a soft jaw set with holes in it and then an adjustable little stop plate with holes in it. It can be screwed into position. Also have a variety of other strategies. Got a little end stop here that extends just a little bit longer, and a variety of other different strategies, and a probing routine that can automatically adapt to any of these left-hand X0 positions. So the probing routine basically starts outside the area of the vise and then moves across, and wherever the 0 happens to be, let's say that, I'm kind of weird to try to do this and not get in the way of the camera. Let's say that I wanted my 0 to be there. The probe would start here and move until it hits the block. So the probe system, the Renishaw probe on the Haas, is one of the most important parts of the system when it comes to increasing speed of setup, reducing setup time, and of course the accuracy is superb. These things are accurate easily within tenths, at least from what I've heard. Haven't independently verified it, but it's close enough for me. So the VPS templates that Haas provides are useful, but they're limited. They require a lot of manual fiddling. The program assumes that you kind of manually position the probe approximately correctly, and then it'll initiate a measurement. I want more automation than that. I want one-button probing. So I always mount devices in the same place. So the system, even if the 0 is off by a few thousandths, the system always knows roughly and approximately where the vices are, and roughly and approximately where to start probing. I also use precision 1, 2, 3 blocks. These are precision ground. They're 1, 2, 3 blocks with no holes in them, and yes, those do exist. And I actually measured it with a really nice micrometer, and yes, it is 1 inch within a tenth or so. And so I can probe the top, left side, and back, and then subtract an inch for Z and get my 0 position. And I wrote a set of probing routines. I have quite a few probing routines. I've gotten kind of comfortable writing G-code for probing routines. And I use a lot of what's called protected moves. And a protected move, unlike a rapid move just moves. And if the probe encounters an obstacle, it will be destroyed. A protected move activates the probe, and if the probe encounters an obstacle on the way, it'll stop and flag an error. So here's a program that's set up to automatically probe the 1, 2, 3 blocks in the left and right vices, and these are work offset 3 on the left, work offset 1 on the right. I have a set of, I think, 15 or so work offsets, standard work offsets. Each one has a different reason for being used. They aren't always the same position, but they're similar enough that similar strategies can be used for working with them and for probing them. So here's my probing routine. Rapid move to a safe position, protected move down, measuring move to the right, rapid move up, which is always safe, probe, go back, probe the back surface, rapid move across, which is safe, protected move down because who knows what might be down there, then probe the other block. I probe before every time I change a setup, I probe it, and even if the setup has been in the machine overnight, even though the homing switches on the Haas are claimed to be highly accurate, I still probe every time I turn the machine on, because once it's been automated to this point, why not? It's free. It's a little bit of extra safety. For many of my parts, I use what I call tooling plates, which is a type of fixture that is used primarily for second operations. In many cases, the first operation is take the blank, drill some holes in it, then screw it to the plate to cut out the profile around the outside. And I have a variety of different tooling plates for different situations. And one of the things that I do when I'm setting up to try to speed up the setup is that each part number, each set of tooling plates has its own probing routine. So obviously, or not so obviously, but obvious to me, that if my 0 is set at the bottom for making operation 1, I certainly wouldn't want 0 to be at the bottom of the tooling plate. I want 0 to be at the top of the tooling plate, but X and Y stay the same. So I have a set of probing routines, one for each setup, where I can put in my 2 tooling plates and then just call up the probing routine and boink, boink, get the Z position or the Z coordinate to set the Z0 on top of each one of these tooling plates. And once again, it's all about improving setup speed, making things go faster. So I've got the 2 tooling plates mounted in the vices, and I've loaded the probing program. And now, pretty much one button, rapid move to a safe position. Now turn on the probe, start the probing cycle, measure Z, move to the second part, measure Z. They should be pretty close to identical since the vices are pretty close to identical, but when you're doing an automated probing routine, hey, why not? Might as well just measure everything, even if it probably for this operation didn't need to be measured. A couple of more comments about the overall operation of the machine. In general, I'm used to it. I'm fast. I can pretty much get anything I need accomplished with a minimum number of steps. The modal operation still drives me crazy. Even after 10,190 machine cycles, pretty much every time I touch it, it says wrong mode. And I have a feeling that, you know, if I use it for another 10 or 20 years, it'll probably say wrong mode 10 or 20 more thousand times. So I really, really wish it didn't have that modal behavior, but there's not much I can do about it except to complain a little bit. The user interface is still maddening and frustrating. I realize that inertia is strong in the CNC world, and training is sometimes an issue. If a manufacturer changes the behavior of their user interface, machinists and shop owners will complain, oh no, now we need more training, now we don't know how to use the machine, and so as a result, bad ideas tend to last forever. While on desktop software, user interface design continues to evolve, and I'm a desktop software user, I'm a computer programmer. I get used to the way desktop software behaves, and the backward, incomprehensible, bizarre way that CNC machines work, yeah, I can get used to it, but it's never pleasant. It never feels right. It always feels wrong, but you know, as annoyances go, that's a pretty petty minor annoyance. As I said before, the machine works exceptionally well, and I really am happy that I got it. I think it's just a great machine. So one other thing that I did, I saw it, and I'm not absolutely sure that this is necessary, but it certainly seemed like a reasonable idea. I saw it on a YouTube video. One of the YouTube machinists recommended putting in an auxiliary filter on the coolant system. And let me take the camera off the tripod and move it around and show you what I did. With a little bit of plumbing and a little bit of ingenuity, not that much, I managed to put in a cartridge filter. I don't use a super fine filter, not for like drinking water quality, just fine enough to catch the stuff that passes through the screen that Haas provides. The screen catches large chunks, but it still lets smaller particles through, and it seemed like adding this extra filter would give me a slight bit cleaner coolant. Speaking of cleaner coolant, I also got one of these coolant skimmers. Since the Haas sells a skimmer, but the skimmer that Haas sells is for the VF machines, for the bigger coolant tanks, and they say it doesn't really fit the Mini Mill. So I got this guy, and it kind of drags a hose through the coolant, and it seems crudely made, but works actually surprisingly well. Over the almost 2 years that I've had the machine, I've been little bit by little bit refining my tool path, refining my machining experience, learning what I can get away with, breaking cutters because I'm too aggressive, turning up the feed when I'm too wimpy, and just generally making incremental improvements so that every run of parts comes out just a little bit faster than the one before it. I'm also getting a little more serious about measurement. I now have a reasonably complete set of precision measurement tools, and am getting a little bit more picky about the tolerances I hold, even though for many of the parts that I make are not supercritical parts, and it's really not necessary to hold high tolerance. still, it's just almost like playing a game. It's almost like, well, how good can I make them? Little bit by little bit, as I understand the machine, understand the tools, understand the machining process, I'm getting to tighter and tighter tolerances. Plus and minus 5 is no big deal. I can do that when I'm being sloppy, and I can hold 1,000th if I'm careful. And of course, I understand that, you know, some machinists that work in tenths will say, oh yeah, but you're not a real machinist. And well, yeah, I'm not a real machinist. I'm a semi-retired engineer with a home shop, but my parts are good enough. They do the job. My parts are good enough for the designs that I design, and my machines work well, and my customers are happy with them. So I think that will pretty much do it for the review. I'll probably end this video showing a little bit of HSM machining with a cutter from Lakeshore Carbide called the aluminum shredder roughing cutter. It's basically just one of those kind of like corncob roughing mills, solid carbide 3-flute roughing mills. A lot of the parts that I make are basically profile cut out of sheet material, or in my case rectangular bar material, and many of the parts are basically profile cuts. When I started doing this, when I first started doing this on the Bridgeport, the profiles were just cut and the offcuts just fell off, and I didn't care because that's the way I knew how to do it at the time. But now with this more sophisticated machine, especially with a chip auger and 10,000 RPM spindle, if I tried cutting one of my parts as a profile only, the offcut sometimes gets caught in the cutter, sometimes gets flung at the wall of the machine, sometimes breaks the cutter, sometimes damages the parts, sometimes falls in the chip auger and gets jammed. So I've switched away from doing profile cutting, and now on all of my parts I basically use an HSM cycle. This is high-speed machining for those who don't speak acronym, and it's a kind of a modern development in machining. Old school machinists never used this on old manual machines, but on the CNC machines of today, with the toolpath software and the high-performance machine control, there's a technique called high-speed machining that's designed to maximize the rate of material removal using a geometric figure called a trochoidal path. And basically it just kind of goes as it eats away at the material. So that's it for me talking. I'm going to probably just close out this video, put the GoPro in the machine, run a cycle, do some HSM on the parts that I'm making now. And as always, thank you for watching. It's been fun.